Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the residence time distribution functions for advanced reactor design. So the residence time distribution, sometimes termed as the probability distribution function, is a function which describes the amount of time a fluid element could remain within the reactor vessel. Now, in order to achieve this analysis, we have to perform what's called tracer response techniques. And we're going to briefly discuss the two types, but more importantly, we're going to see why and how this is actually applicable for us to design real reactors. Because ultimately what we want to know is what is the distribution of the molecules within the reactor from the inlet to the outlet. What do they actually do inside the vessel? Now, different reactors will of course have different residence time distributions. Now this can even apply to, say for example, we had CSTRs. So the residence time distribution of one CSTR would be different than if we had, say, CSTRs in series. And what I mean by that is if we have one CSTR, which then feeds into another CSTR, then the residence time distribution for this reactor will be different for this reactor, because the composition will change as time progresses. So that's something that you have to consider, is it's not just the vessel, it's what is the configuration and the number of vessels within the system. Now, non-ideal reactors can basically be categorized by determining the following set of variables, because what we're about to see here are not featured in ideal reactor models. Now, there are a series of videos on the YouTube channel which cover the modelling and the design of ideal reactors, most commonly CSTRs and batch reactors. I'll put a link in the description to them and you can check those ones out. But alternatively, we have our reactor design course, which again I'll put a link in the description, and that goes into all the details from the fundamentals to the most advanced reactor design methodologies required for chemical and petroleum engineering. But the variables or the characteristics that we need to consider here is firstly the residence time distribution function. And that's what we're going to spend our time on in this lesson, is we're going to discuss what the E of T function is and how it is applicable to the residence time distribution. Then what we have is what's called the mean residence time, sometimes denoted by T bar, or usually T subscript M. It just depends on the nomenclature that is being used from your reference source. Then we have the cumulative distribution function, and this is denoted as F of T. And what this tells us is the culmination of the function as we go per unit time. So for example, and we'll see these in just a second, but your cumulative function would go something like this. It doesn't decrease. Whereas our E of T function, so this would be F of T, whereas our E of T function can come up and then come down. So F of T, the clue is kind of in the name, cumulative. So it accumulates over time. It takes into account the previous values from that particular iteration. And then finally we have the variance. Now the variance is very, very important, because what that will allow us to do or categorize is what is the change, the subtle changes in the fluid elements as we progress through per unit time. Now, as I says, we would look at these in a lot more detail in our other videos and in the course, but here what we're interested in is looking at the residence time distribution function. But all of these parameters are determined through tracer injection responses. So this is all experimentally done. Whenever you solve these problems, it's always from live experimental data. Now, if we hone in on the tracer response technique, then this is just a general schematic of what we are trying to visualize when we do this. Is that we have a steady state flow which comes in at the inlet point and leaves at the outlet. We then have a fixed vessel volume. So what we need to ensure is that we fix the volume within the system. And generally speaking, within the reactor, we can assume that the volume is fixed. Now we have our volumetric flow rates of V, which is in meters cubed per second. And what we then have is we have our detector at the end or the outlet of the vessel. And what that's going to detect is the tracer that we inject at the beginning, right at the inlet of the vessel. And what it's doing is it's timing how long it takes for the tracer to then leave the system. So what this will then allow us to do is map out what the concentration change is per unit time. So we would create what's called a C curve. And the tracer concentration in the outlet has to be measured by the detector. Usually the detectors are things like UV detectors, but we have to ensure that the tracer is inert to the actual system. We don't want it to interact and react with our material. We want it to behave in such a way that replicates the material that's actually going into the vessel. Now, the two types of responses and types of inputs is known as a pulse input or a step input. Now, in either case, the system is the same. We have our feed and we have our effluent, which is our inlets and outlets. We will have our injection points and we will have our detector. Now, the key difference here is in the way in which the tracer is being injected. A pulse injection is one in which we have a sudden amount of tracer, a fixed amount of tracer that is then injected and then stops. So we can see here that our pulse injection, we have a high concentration and then a low concentration till we go to zero. This is at the start. That then means that the pulse response must then, as time progresses, the detector will start to detect small amounts and then it will gradually increase up to a maximum and then it will decrease off again to zero once all the tracer has passed through the reactor. A step input, on the other hand, is one in which we put in the tracer, but we keep the concentration the same. So we keep adding in the tracer. And that then means that the response, so the step response, will increase from time zero up to a certain point, and then it will taper off, because at this point the concentration becomes constant. And it becomes constant because we keep adding in the same amount of tracer. So you can see the difference, and depending on the type of system, the data that you would like to know will dictate which type of response you will go for. Now, if we link this back to the residence time distribution function, so that is our E of t curve, then depending upon the type of reactor and the tracer, the response will be different. So the equations for this is our typical E of t curve. So we have our resonance time distribution, so that's our E of t curve here with respect to time. That's what the t is, that's for time. Now, our curves will be able to be analysed as an integration. So our pulse input, our E of t curve, is the volumetric flow rate, so V, multiplied by the change in the concentration of the tracer with respect to time, divided by N naught. So that is the initial concentration of the tracer, the initial amount of the tracer. That will then allow us to determine and analyse the E of t curve for a pulse input, Whereas with a step input, we have a differential equation whereby it will change with respect to time, as does the pulse input, but again, it will taper off. But our step input for the E of t function will be the ratio between the initial amount that leaves the detector divided by the amount that was initially introduced into the system. And again, this is for a step input. Now again, this is just something a bit extra on top of the residence time distribution lesson. If you want to know all the details and more about these types of responses, when they're used, how we actually derive these equations, then I highly recommend that you check out our new updated reactor design course. I'll put a link in the description to that. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept of residence time distribution for real reactor design. If you liked this video, please consider liking and subscribing to the channel. It really helps us reach as many chemical engineering students as possible. If you'd like to connect with me directly on LinkedIn, you can scan the QR code up here, and please feel free to get in touch either through LinkedIn or via email. Thank you for your time, and we look forward to seeing you in another video.